So derivatives of integrals. So this is the first fundamental theorem of calculus. So if you have an integral from 3 to x, I should do 0 to x, because they like 0. So f of t dt, okay, and that's g of x, right? Then g prime of x will just equal f of x. Right? We did this the last time, or 2 times ago. Then g double prime of x will equal f prime of x. So say I told you that we had something like I wanted to find g prime at pi over 3 and g double prime at pi over 3. Suppose I wanted to do something like that. Got it? Got it. Good. So, g prime of x would be 1 plus cosine square x times the derivative of cosine, which is minus sine. So if I wanted to find g prime of pi over 3, I now plug in pi over 3, right? Would be 1 plus cosine squared of pi over 3 times minus sine of pi over 3. So cosine of pi over 3 is a half. So cosine squared would be a quarter. Right? So this would be 1 plus 1/4 times minus radical 3 over 2. And I'm not interested in what that is. And then if I wanted to find g double prime of pi over 3, I take the derivative of this, which is product rule. Right? So I have g prime of x would be 1 plus cosine squared x times the derivative of minus sine, which is minus cosine, plus minus sine of x times the derivative of 1 plus cosine squared, which would be 2 cosine x to the 1 times minus sine x. This is very tedious. Okay, and that's g double prime of x. This comes from the product rule. You look scared. Either of you. Got it? Alright, and then you just plug in again. So g double prime of pi over 3 would be this. 1 plus a quarter times minus a half plus minus radical 3 over 2. 2 times a half times minus radical 3 over 2. It doesn't really matter. Okay? And you simplify it. Okay? Everybody good? So that's a typical type of thing you could ask, because we're testing if you see the connection between the function, the integral, and the derivative of the integral. Okay? So when you do the derivative of the integral kind of goes away, especially if you just go from 0 to x, or any constant to x. So far, so good? Okay, you guys look happy. Alright. We could give you, I'll wait a minute. I'll wait till somebody's got that down. You know it'll be on the video later. Alright, so, another thing you could do with this fundamental theorem stuff, I did some of last time. And I tell you this is f of x, f of t. give you something like that. So we did this last time. So remember what this means. This means g of x basically means the area until you get to x. So g of 4 would be the area up to 4. G of 6 would be the area of 6, which would be this area minus that area. Right? G of 8 would be the area from here to here, and so on. So if I say, where is g increasing? Can you see that back there, Paige? Where did Nia go? She was here.
Having them.
Oh, yeah. So she just sort of checked in.
Yeah.
Okay. It's nice of you guys to show up for 30 seconds. Sorry about that. Where is g increasing? G is increasing, well, remember from last semester, g is increasing when g prime is positive. And what is g prime of x? G prime of x is f of x. So wherever f of x is positive, g prime is increasing. So that would be 0, 4, and 6, 8. Does that make sense? I want to know, where is g increasing? To know where g is increasing, I need to know where g prime is positive. Well, g prime is just f. So f is positive between 0 and 4, and between 6 and 8. So what if I said, where is g concave up? Or concave down? It doesn't really matter. So g is concave up, where g double prime is greater than 0, right? So g double prime is greater than 0. Well, if g prime is f, then g double prime is f prime. And f prime is just the slope. So that would be from here to here, and from here to here. That's the two places where f has got a positive slope. So 0 to 2 and 5 to 7. That makes sense? I like these kind of questions. I didn't put them on my exam last semester, but they're kind of okay. Some people really like them, some people don't like them at all. The AP loves them. There's one in every AP exam. What is the next step? Okay, you feel we understand that stuff? You sure? Okay, so we're going to learn something new now. I just want to make sure everybody feels okay about this. Last chance. Yeah? Thinking about chemistry. No chemistry. No chem thoughts. Everything's empty. Alright. We're going to learn something new. Substitution method. Substitution rule. Same thing. It's really a method more than it is a rule. What are my four favorite rules? Product rule, chain rule, quotient rule, jar rule. There you go. Gotta get the order right. But not in that order. Okay. I know, he's very old school. All right. So, substitution. So now we're going to start to learn how to do hard integrals. So we've only really been doing very simple integrals so far. So you need the substitution rule, substitution method, when you want to work backwards from the chain rule. If you haven't seen, this is what you're going to use when you have an integral that essentially has two things in it. And one of the things in the integrand is the derivative of the other thing in the integrand. So for example, say you have the integral of I think the WebAssign tries to teach you how to do this, but I'll do my flavor of it, my version of it. All right. So how would you do the integral of this? Well, one thing you could do is you could expand this out to the 10th and then distribute the x squared. So that would be easy if this was, say, squared, because then you could just sort of FOIL it out. But to the 10th is a bit messy. But then you could notice something. X cubed, the derivative of x cubed is kind of like x squared, because you just 3x squared, right? So if we let u, we like to use the letter u, equal 5 plus x cubed, and du dx, the derivative of u, would be 3x squared. And there'll be a reason for this in a second. Then cross multiply this and get du is 3x squared dx. So 1/3 du is x squared dx. So far so good?
Why take out the 1/3?
Why take out the 1/3? All right. I look at this integral and I say, I'm going to substitute things. So I have 5 plus x cubed. So if I let this be u, this would just be the integral of u to the 10th, which is trivial. Okay? But I'm stuck with an x squared and a dx. So I take the derivative and I say, I've got 3x squared dx. But I only want to substitute for x squared dx. So if I move the 3 to the other side, now I can go over this integral, and I can say this is u to the 10th. And this is 1/3 du. Pull the 1/3 out. And that's an easy integral. So far so good? Okay. So what's the integral of u to the 10th? U to the 11th over 11. So that's 33 down there, right? Because you got a third and you got an 11th. Can you all see down there? And then substitute back, so you would get 1/33 5 plus x cubed to the 11th plus 6, of course. Okay? And the 33 comes because this is 1/3 times 1/11th. And double check that in your head. So take the derivative, you get 11/33 5 plus x cubed to the 10th times 3x squared. So notice, right? That's a third. That cancels with the 3, and you get the x squared and the 5 plus x cubed. So what the u substitution does is it undoes the chain rule. It basically looks at this integrand and says, there's a chain rule going on in here. So I'm going to work the chain rule backward. So let's do another example. Suppose I had sine x. All right, so I would do u substitution. So I'm looking for something and its derivative. Now I look and I say, well, the derivative of sine is cosine, the derivative of cosine is sine, so how would I know which to do? Well, this is under the radical, so that's causing me more irritation. So I'm going to let that one be u. I'm going to let u equal 1 plus cosine of x. And then the derivative would be minus sine of x, which is almost the same thing as sine of x, right? So if I cross multiply, I would get du is minus sine x dx. And tonight I'll put up the pages from my book that do this u substitution. So you can work through lots of examples. So now I come over here and I say, well, all right, I could make this square root of u, and this would be negative du, because du is negative sine x dx, so negative du is sine x dx. Confused?
Yeah.
Who's confused? All right, so the idea is you want to look at the integral and you want to put u into one part, and then the rest of the part has to be some form of du. Usually you play with constants. Okay? So you can turn this now into a very simple integral. So I look at the beginning and I say I've got the square root of 1 plus cosine x, and I got sine x. I know the derivative of 1 plus cosine x is minus sine x. So this is basically minus sine x. I'm just off by a minus sign. So if I let u be this, and then du is minus sine x, then I can substitute everything in here and make this, remember this is an easy integral, right? This is just u to the half. We'll do like 3 more of these and then you'll get good at it. So that becomes u to the 3 halves over 3 halves plus a constant, and then you substitute back. Minus 2/3, 1 plus cosine x to the 3 halves, plus c. See, what's going to happen in integration is you're going to look at integrals and you're going to say, I have no idea what to do, and you're going to start trying out all of your tricks and see if you can come up with one that'll work. Yes? What happened to the minus sign? So this is, my du is minus sine of x, but I've only got positive sine of x in here. So when I substitute, I use negative du. Okay? To get rid of the minus, because this is minus here. Right? So minus du would be positive sine x. Okay, that's why I have the minus sign here. Okay? Let's do some more of these. After about 3 or 4, you'll start to get the hang of them. You'll see. Maybe not. So the integral of x cosine x squared dx. Whatever. I can keep my job for a couple more years. And we'll see. Alright, so let's do some substituting. Well, I see the cosine. I can't do much with cosine. If I said I let u equal cosine, derivative of u is sine, and there isn't any sine in here. But if I let u equal x squared, see, the problem is, I could do the integral of cosine x. That's easy. I can do the integral of x or some x squared, but the cosine is sort of messing things up. So I'm going to let u equal x squared, and then du dx is going to be 2x. Why do I want to do that? Well, I want to get rid of this problem. Now I look at the integral and I integrand and I say I've got x dx. So if I cross multiply, I've got 2x dx. I only want to substitute for x dx, so I just divide by 2. Okay. Now I go here and I substitute. I substitute for cosine of x squared, I get cosine of u. And x dx is going to be 1/2 du. Put the half outside. I could put the half inside, but I generally put constants outside of the integral. It's easier that way. Alright, what's the integral of cosine? Sine. So, u is x squared, so this is 1/2 sine of x squared plus c. And if you took the derivative of sine of x squared, what would happen? You'd have cosine of x squared times 2x, right? So that's where that x appears from. So as I said, so u substitution is working this backwards over and over again. So let's give you guys 1 or 2 to practice. Nice easy ones. I know it's new for almost all of you, so I won't give you the killer ones yet. That's for the second half of the lecture. Believe me, you guys will get the hang of this very soon. It's really not that bad.
I'm so glad that way.
Okay? There's your first two. Give you guys a couple minutes. So I look at this and I see sine to the fourth x cosine x. So I'm going to need u substitution. And I say to myself, well, if I let u equal cosine, the problem is du would be sine, sort of. And that would be du to the fourth, which doesn't make any sense, right? I'm only used to 1 dx at a time, or 1 du. So du to the fourth would be sort of painful. And if I let u equal sine to the fourth, the derivative of that is 4 times sine to the third times cosine. That's not what this is. But if I let u just equal sine, then du would be cosine. Instead of writing the dx down here, I'm just going to cross multiply right away. Okay? You can skip that step if you feel the need to. And now it's easy to substitute. I say, well, this is u to the fourth. And this is du. Easy? So that's now u to the fifth over 5. And then I substitute back, and I get sine to the fifth x over 5 plus c. How are we doing that one? Of course, it's easy if I tell you to use sine, right? So in the beginning, the mistake people make is they're not sure which one, or they're trying to substitute for the whole expression, which you don't need to do. You don't need the power, because you can always do u to a power. So don't worry about substituting for the power, okay? But you understand the idea. So some general rules. If you have something to a power, and you have something else that's not to any power, just a power of 1, still a power, okay? Then the thing with a higher power is almost always going to be u. But usually you can ignore what the power is. Okay? The second thing is if you have two things in the integral and they're 1 power apart, x to the 10th and x to the 9th, then the higher power will be u and the lower power will be du. We'll do an example of that in a minute. Alright, what about here? I see cosine of e to the x, and I see e to the x. So if I let u equal cosine, there's no sine in here. But if I let u equal e to the x, du is e to the x dx. So this now just becomes integral of, that's cosine of u, and e to the x dx du. You like that one? So that's just sine of u plus a constant. So that's sine of e to the x plus c. By the way, some professors are very fussy about the whole plus c thing. And they take off points if you don't write the plus c. So try to remember it. When you're done with your exam, look at all your integrals. And don't forget to just write plus c after them. But not for the ones where you take the derivative of the integral. Okay? Don't mess that up. Let's do some more of these. So remember what I told you. You look for something to up. And if they're 1 power apart, the thing that's to the higher power will be u, and the thing that's to the lower power will be du. Okay? Higher power will be u, lower power will be du. Let's let u equal 6 plus x to the 10th. Why do I choose that? Because the derivative of x to the 10th is something x to the 9th. And the derivative of 6 is just going to go away. So du would be 10 x to the 9th dx. You all see why I can put the dx over here, right? It's du dx, and then I just multiply across. So now I look at the integrand, and I say, well, this will become u to the fourth. So I just have to play with this a bit. So I have 10x to the ninth. So if I divide by 10, I get x to the ninth. So now I substitute. This is u to the fourth. X to the ninth dx is 1/10 du. So that's 1/10 u to the 5 over 5 plus the constant. So u is 6 plus x to the 10th. So this is now 6 plus x to the 10th over 50 plus c. And yes, you could have written 1/10 in the 5th and separated them. That's fine.
I got enough people out.
Okay? How are you doing this one? Starting to get the hang of it? Good. Should I kill you with some hard ones now? Sure. Thank you. No problem. Oh, yeah, I'm sorry. I wrote that wrong. Thank you. That's what I meant. Thank you. All right. There's one. What should we let u equal? Good choice. Element of x, also known as log. Why is it so hard for you to look at the letters ln and say the word log? I mean, lots of things in English are not pronounced the way they're spelled. Okay? So, none of you can pronounce February correctly, so some of you can pronounce February correctly. Most of you say February, which is not the way it's spelled, so there you go. Alright, so the derivative of u is 1 over x dx. And look, I have 1 over x dx. That's this. Right? That is 1 over x dx. So this is just sine of u. Integral of that is minus cosine of u plus a constant, and then substitute back minus cosine of log x plus a constant. How are we doing that one? Yes? No? Love and life? Not love and life? All right. Time to give you one slightly harder. Okay. U substitution. Now try the substitution. Let's let u equal cosine x. Now, how do I know to let u equal the denominator? Well, if I let u equal sine x, I'll have du in the denominator. That doesn't do me any good. I don't know what to do with the d down there. It's got to be up in the numerator. But if I let u equal cosine x, then du minus sine x dx.
That's what I meant.
So I can now rewrite this as minus du over u. And that is log. Yes?
Is that like a general rule when you have a fraction and you're always going to find the u in the denominator?
That's a very good rule. So yes, if you have a function over a function, u will be in the denominator. It can't be in the numerator. Okay? Because if u is in the numerator, du, well, almost always. Okay? Because here, right, sort of was in the denominator, but not really. Okay? They're really multiplied. This is really sine of log x times 1 over x dx. Okay? But generally, you can't have du in the denominator because there's nothing that you can do with that. That's nonsense. So you have to have it up in the numerator. Alright, so this is negative log of u plus a constant. Substitute back. I suggest you memorize what the integral of tangent is. Okay? So one to add to your pile. And you should be able to figure out cotangent x once you know tangent x. Okay. Yes?
How did you get the du over u log of u?
How did I get from here to here? Well, what's the derivative of natural log? 1 over x. So this is 1 over u. Right? So the integral of minus du over u, right, is the same as minus 1 over u du. So that's why it's natural log. Okay? Here's one that's annoying. So we'll do this one as a t, because this one's slightly annoying. What if I let u equal tan x? Well, du would be secant squared, which doesn't do me much good, because I got secant to the 10th. What if I let u equal secant? What's the derivative of secant? Secant tangent. So what if I rewrote this as secant to the 9th x times secant x tan x dx. So I just pulled out one of the secants. We could be quite nasty if we need to. We've got even more evil ones up our sleeves. Now, let u equal secant x du secant x tan x dx. So far, so good? Sure. Once I showed you. Okay. Well, you get there on your own. So this now becomes u to the 9th du, which is u to the 10th over 10, plus c, and that's secant of 10th x over 10 plus c. I have one more type to show you guys. Suppose you have something that looks like that. Now, if I let u equal x, du is just dx. That doesn't do me much good. What if I put the x back under the radical? Then I'd have x squared and x cubed. That doesn't do me any good. And if I let u equal 1 plus x, what if I let u equal 1 plus x? And du is just dx, right? What do I do with this x? Well, if u is 1 plus x, then let u minus 1 equal x. And now this would become u minus 1 times the square root of u and u. Yes? Surely. I look at this and I say, if I let u equal x, du is dx, which is just 1. That doesn't do me any good. But if I let u equal 1 plus x, so this will now become the square root of u. This is just u minus 1. Now I could just distribute that square root of u. This would become become u to the 3/2 minus u to the 1/2 du. So how do I know to do that? They're the same power. I look and I say, if you have an x and an a plus or minus x, that's the trick that you use. Okay? So if you look at the integral and you have one of them is some constant plus or minus x, or the other way around, x plus or minus a constant, and the other is just plain x, this is the trick you're going to use. The whole next month is going to consist of techniques of integration. It's like you have little tools in your toolbox. You can figure out which one to use. So right now you've got a second tool. And we're going to do integration by parts, we're going to do partial fraction, you get about 5 tools when we're done. Then the trick is just which one do you use, and my advice is you try one after the other until you get one that works. Okay, so this you can integrate. See here, if you distributed the x at the beginning, you would have had this, and that you can't do anything with. Okay? But here you can, because this, oh, I put your hand up. This is just u to the 5/2 over 5/2 minus u to the 3/2 over 3/2 plus c, and then substitute back. So you get 2/5, 1 plus x to the 5/2 minus 2/3, 1 plus x to the 3/2 plus c. Okay? Teachers like that one. Sort of an advanced u substitution one. I know I had it when I did integration back in the day. Which I took right here, so. You guys had a chem exam tonight? Alright, so we'll stop a few minutes early. See everybody on Wednesday.